Hi, I'm Dave, and I'm going to try and do a video thing of me solving one of these integrating factor problems from lesson 7. I don't know if it'll work because I don't do this and I've never done it. So here we go. So it'll be crooked because I can't do anything. So this is first order linear. Linear. And it won't be exact, most likely just out of the gate. You want to make it exact by multiplying the whole thing by an integrating factor. And in general, those are hard to find. There are different techniques. But when you have a first order linear equation, you can always, your integrating factor is always of the form e to the p integral of p of x, in this case t, dx, if your first order linear equation is in the form y prime plus p of x y equals, can you see that? Yeah, f of x or q of x or whatever you want. Okay. So the key is I have to have the coefficient of my y prime term to be a 1. So here what I'm going to do, I'll change colors, is what I'm going to do. So here I'm going to divide by, to get this coefficient of 1, I'm going to divide by the 3t. And I get 1 over 3ty equals t to the 6th divided by 3t, be t to the 5th over 3, right? Yeah. Good, yeah, good. I can do algebra. Okay, so now that your coefficient of the y prime is a 1, the integrating factor is mu, be a function of t in this case, e to the integral of p of t dt, where the coefficient of your y term, right here, that's your p of t. So this will be, angles weird, equals e to the integral of 1 over 3t dt, which is e to the 1/3 natural log of t. And of course you've got plus a constant, but when we're doing integrating factors, you can assume the constant is 0. And then this is e to the natural log of t to the 1/3, and e to the natural log cancel, and so your integrating factor is t to the 1/3. Factor. Yay. Okay, so that means if we multiply this entire, this equation right here, the one that has a coefficient of 1, not the original one, but the one we're actually finding the integrating factor from, this guy right there, the whole equation, then it'll actually make the equation exact, and then you can, do your techniques to find the solution, your exact techniques to find a solution. I like doing kind of, in this case, it works out a lot even nicer, and I'll show you that. So but I guess let's hold on, let's continue. Let's do this. So multiply the whole thing by the integrating factor, and we get t cubed dy dt plus t cubed times this guy will be t squared over why can't I do, oh sorry, this is t to the 1/3, right, t to the 1/3, then this is magic tape that's not being so magical at the moment. So now we've got t to the 1/3, yeah, that was wrong, t to the 1/3 divided by 3t. We can do algebra to clean that up a little bit, times y equals this guy times t to the 1/3. T 5th over 3 times t to the 1/3. Hi. Sorry, I had to adjust a few things, but here we are. And let's clean this up just a little bit. So we have t to the 1/3. I'm going to call this y prime. T to the 1/3 minus t, or divide by t, is t to the 1/3 minus 1, which is t to the negative 2/3. So 1/3 of t, right? Yeah, to the negative 2/3 times y is equal to t to the 5th times t to the 1/3 is t 1/3 plus 5, that's 15/3, plus a third is 16/3, right? Yeah. So arithmetic. Now, notice something. Well, here's something that will always happen with first order linear equations when you use the e to the integral thing as your integrating factor. It'll happen other times too, but definitely always in this case. See, notice there's a product rule hanging out in here. Product rule. Remember, product rule is first times derivative of second plus second times derivative of first. If I call this my first, and if I call this my second, then notice that, let me get this out of the way for a second, that this, if I take the, for example, the derivative of what I'm calling my first, and there's what I'm calling my second, I have first times the derivative of the second times derivative of second plus, I want to do second times derivative of first. Second is y times the derivative of the first is 1/3 t to the negative 2/3. That's exactly what I have here. So what I'm saying then is, I should put caps on. What I'm saying then is that this, you could call it reverse derivative factorization. I don't know, that's not an official word, but I have the derivative of t to the 1/3 y, that's what this left-hand side equals 1/3 t to the 16/3. Now this little thing will always happen if you use e to the integral junk as your integrating factor for a first-order linear equation. Now this is good because then integrate, and that would be just great. The integral and derivative cancel each other, right? So you'd be left with t to the 1/3 times y equals the integral of this guy over here, 1/3 times 16/3 plus 1 is 19/3. Sorry if I'm writing crooked, I'm at an angle here. Divided by 19/3. And so that's 1/3 times 3/19 is 1/19 t to the 19/3. And then, so that's your implicit solution. If you solve for y to get an explicit solution, you'd have y equals, and then you've got a plus c, of course. T to the negative 1/3 times all this gives you y equals 1/19 t to the 18/3, which is 6, because 19/3 minus 1/3 is 18/3, which is 6. Arithmetic and stuff. And then, plus c times t to the negative 1/3. And that's our solution. And you can check by plugging it in. Right there, yeah. Can check by plugging into original equation. Anyway, so there it is. It's good stuff. What is that? I don't know. It's good stuff, and I hope you had fun. I know I did. And here is a Pyraminx. Okay, have a good day. Bye-bye.